Welcome viewers. Today's topic is Laurent series. Viewers, we have learned that a function f of a complex variable z can be represented as a power series when the function is analytic in a domain, let us say D. In the domain D, we can draw a circle of radius r1 centered at say z is equal to a. Then we can represent this function f of z in powers of z minus a, and we can say that this series converges in a and its radius of convergence is r, and in this circle there is no point where function is not analytic. But what happens if the function is analytic at some points in this domain? Can we represent still this function fz as a power series? So this is the question we are going to answer today. Now let us say we have a function f of z which is analytic in two concentric circles C1 and C2 with center at z is equal to a. The idea here is that this function fz may not be analytic at some points inside the bigger circle of radius r1. Then all those points can be enclosed in the circle, smaller circle of radius r2, and then it is the function will be analytic throughout in this annular region. So that is why we say if fz is analytic on two circles C1 and C2 with center at z is equal to a, and in other words we can write it as that function is analytic on z minus a is equal to r1. It is a circle of radius r1 center at z is equal to a, and another concentric circle centered at the same point a and of radius r2, and together with this fz is analytic inside this annular region. Then fz can be represented as sum of these two series. The first series is in powers of z minus a, and this n is positive, while in the second series it is in powers of z minus a, n being negative. So first series n varies from 0 to infinity, while in the second series n varies from 1 to infinity. In the first series z minus a appear in the numerator, and here it appears in the denominator, and with this in the expanded form the function fz can be expressed as b0 plus b1 z minus a plus b2 z minus a square plus and so on, and the second series will look like as c1 divided by z minus a plus c2 divided by z minus a square and so on. Here the coefficients bn, they are expressed as 1 upon 2 pi I integral over C, a closed curve, and the integrand is fz star divided by z star minus a raised to power n plus 1 into dz star. Here z star is a point on this closed curve C, while the coefficients Cn's in the second series, they are obtained as 1 upon 2 pi I integral over the closed contour, and the integrand is z star minus a raised to power n minus 1 fz star dz star. Here again this point z star will lie on the closed curve C. Now to prove this result, we consider the function fz as analytic inside this annular region. So we consider a closed curve C star as this outer circle in the anti-clockwise sense and inner circle in the clockwise sense, and then we join these two circles by cut, and there are two lines parallel to each other, the one going in the forward direction, another in the backward direction, and accordingly the C star will be if we start from this point, will look like a closed curve starting from this point, moving along this line, then moving along the outer circle in anti-clockwise direction, then coming back to this point along this line but opposite to this, and then moving along the inner circle in clockwise direction. So, this makes the curve C star. It is a closed curve, this being a cut, and function is analytic throughout in this region. With this definition to C star, we can apply Cauchy integral formula, and according to this, the analytic function f z in this domain is 1 upon 2 pi I integral over C star, and the integrand is f z star divided by z star minus z dz star, where z is any point inside this region where f z star is analytic and it is inside the closed curve C star. To simplify this expression, we consider C star to be consisting of the 4 curves C1, these 2 straight lines, and C2. So, expressing this C star in these 4 curves will have 4 such integrals, but integral corresponding to these 2 straight lines, they will cancel out each other because the orientation of the curve is just opposite. So, we will be having only 2 integrals, one along this outer curve in anti-clockwise direction and another along this inner circle in clockwise direction, and because of this we will have a negative sign here. This is positive direction is taken as anti-clockwise direction and the negative direction is taken as this clockwise direction. So, we will represent f z in these 2 integrals, and accordingly we write f z as sum of these 2 integrals I1 plus I2. Now, we consider C is simple closed path lying along this annular and Z is a point on this. Now, we will not consider these 2 integrals along this curve or this curve, rather we will consider these integrals along this curve. The idea is you can contract, you can shrink this outer circle to this, since there is no point where function is analytic. So, integral along this curve is the same as integral along this curve, and similarly you can expand this inner circle to come to this circle, and since there are no points where this function ceases to be analytic, so you can expand this to this curve C. I call this curve as C. So, now onwards we evaluate these 2 integrals on this curve C. Now, to evaluate these 2 integrals, I will write 1 upon z minus z star as 1 upon z star minus z minus a by adding and subtracting a in the denominator, and then z star minus a is taken outside and will have 1 minus z minus a divided by z star minus a. Now, on the integral I1, where we are integrating over the outer curve C1, one may notice that z minus a divided by z star minus a, its magnitude is less than 1, because z lies in the annular part and z star lies on the outer boundary. So, z star will be far away than z. So, z minus a over z star minus a modulus is less than 1. So, if this is the case, then the integrand 1 upon z minus z star can be expanded in the by the geometrical series as 1 over z star minus a into 1 plus z minus a over z star minus a plus z minus a divided by z star minus a whole square, and so on. So, here we have expanded this function in powers of z minus a divided by z star minus a, z minus a over z star minus a modulus being less than 1. So, this series is convergent. So, we are writing this integral this part of the integrand 1 upon z minus z star as this. So, this will be substituted in the integral I1. So, we multiply this series by f z star, integrate over the curve C1 and then multiplied by 1 upon 2 pi I. This we do for each and every term. So, first term will give me 1 upon 2 pi I and integrand is f z star over z star minus a dz star integrated over C plus z minus a into 2 pi I, and then the integrand is f z star minus a whole square dz star and so on. Here we have assumed that when we take integral of this, then we can actually integrating it term wise. So, it is this integral is infinite series, and when we integrate, then integrand can be integrated term wise. Of course, we have not proved this so far, but at the moment we are taking it for granted. So, if we express I1 in this form, then these are the first terms, and then after n terms, remaining terms are represented as R and Z, where R and Z is z minus a raised to power n plus 1 over 2 pi I integral C f z star divided by z star minus a raised to power n plus 1 into z star minus z into dz star. Now, as we have done in the case of Taylor series, this expression will tend to 0 as n will tend to infinity, and accordingly I1 will be 1 upon 2 pi I into f z star over z star minus a dz star plus z minus a divided by 2 pi I integral C f z star divided by z star minus a whole square dz star and so on. So, in this way, if we express this coefficient as B naught and this the second coefficient of the coefficient in the second term is z minus a is this one, and we represent it as B2 and so on. So, I1 will be B naught plus B1 z in z minus a plus B2 into z minus a square, and the nth term being Bn into z minus a raised to power n and so on. So, this is an infinite series, R and Z being tending to 0. Here the general term Bn can be given by the formula 1 upon 2 pi I integral over the curve C and f z star divided by z star minus a into n plus 1 dz star. Here I am writing the contour integral over C because I am replacing C1 by C. The expression is given earlier. Then we have to evaluate I2. Now, to evaluate I2, which is 1 upon 2 pi I integral over C2 f z star over z star minus z d star dz star, and here I will consider z star minus a over z minus a magnitude is less than 1, because this C2 is the inner curve and z star minus a will be smaller than the point in the annulus region z minus a. So, z star minus a divided by z minus a modulus is less than 1. So, assuming this, I can expand 1 upon z star minus z part of this integrand as 1 upon z star minus a minus z minus a, and then z minus a can be taken out, and this will be minus 1 of 1 minus z star minus a divided by z minus a. So, this minus will be absorbed with I2, and accordingly if we expand it in geometric progression, we will have 1 upon z minus a into 1 plus z star minus a divided by z minus a plus z star minus a divided by z minus a whole square and so on, and nth term is z star minus a divided by z minus a raised to power n, and this series is a geometric series which will be convergent under this given condition. So, once we have done this, then we can again proceed in the similar manner, that is, I multiply that expression by 1 upon 2 pi I and f z star and then integrate over the curve C2. And if we proceed in this particular manner, we will have I2 is equal to 1 upon 2 pi I and 1 upon z minus a will be taken out, and we will have f z star d z star as the first term, plus in the from the second term we can take 1 upon z minus a square outside the integral sign, because we are integrating with respect to z star and this does not involve z star. So, this can be taken out and we will have integrand of the second term is z star minus a into f z star d z star, and again we have replaced this curve C2 by C. So, this way we can have general term as this and the remaining term are absorbed in the remainder Rn star z. The remainder term Rn star z is written as this. Now, the value of the integral is not altered by replacing C2 by C, this I have already explained, and then I2 will be represented as C1 divided by z minus a plus C2 divided by z minus a square, and nth term being Zn Cn divided by z minus a raised to power n and so on, where the coefficients C1, C2, Cn's they are given by this general formula, that is Cn is equal to 1 upon 2 pi I integral over C, and the integrand is z star minus a raised to power n minus 1 eval and f z star d z star. So, this is my Cn, and then Rn star z as we have expressed it as this, and from here one may notice that f z star divided by z minus z star modulus is less than m, f z being analytic on the curve C2, and modulus of Rn star z will be less than modulus of 1 upon 2 pi I, which is 2 pi, and then z modulus of z minus a raised to power n plus 1 multiplied by z star minus a raised to power n plus 1 into m times L, and L happens to be 2 pi. So, we will have this integral is m times z star minus a divided by z minus a raised to power n plus 1, and since this term is less than 1, this modulus is less than 1. So, as n tending to infinity, this term will become smaller and smaller, and ultimately Rn star z will tend to 0 as n tending to infinity. With this, we have been able to represent the function f z in powers of z minus a, and in the series we have both positive powers of z minus a as well as negative powers of z minus a. So, let us illustrate this with the help of an example. So, here we have to find the Laurent series for the given function f z is equal to 1 upon 1 minus z square with center at z is equal to 1. One may notice that this function f z has is not analytic at z is equal to 1. We can express this function f z in the form 1 upon 1 plus z into 1 upon z minus 1, and I have taken minus outside to make it 1 minus z square. So, this function is not analytic at z is equal to 1 as well as at z is equal to minus 1, but since we have to find Laurent series expansion about z is equal to 1, so we are concerned about its analyticity at z is equal to 1. Now, this is already in powers of z minus 1. So, if we express 1 upon 1 plus z in powers of z minus 1, then we are through. So, to express this in powers of z minus 1, we rewrite 1 upon 1 plus z as 1 divided by 2 plus z minus 1, and then 2 can be taken out and we will have 1 minus z minus 1 divided by 2 raised to power minus 1. And assuming z minus 1 divided by 2 is less than 1 or z minus 1 modulus is less than 2, then this term will be less than, its modulus will be less than 1, and then we will be able to expand it in power series, in powers of z minus 1. So, to do this we write 1 upon 1 plus z is equal to half of minus times z minus 1 divided by 2 raised to power n. N takes values from 0 to infinity. So, we have expressed this in compact form, and this way will simplify it to be n is equal to 0 to infinity summation minus 1 raised to power n 2 divided by n plus 1, and here we have z minus 1 raised to power n, and this gives me the fz representation of 1 upon 1 minus z square as minus summation n is equal to 0 to infinity minus 1 raised to power n 2 raised to power n plus 1 in the denominator, and z minus 1 raised to power n multiplied by 1 upon z minus 1. So, this is in powers of z minus 1. The region of convergence of this series is modulus z minus 1 lying between 0 to 2, because there is another point which is at a distance 2 from z minus 1 where function ceases to be analytic, and that point is minus 1. Therefore, we consider modulus of z minus 1 is less than 2. Modulus of z minus 1 is greater than 0 will take care that z is equal to 1 is not included in the annulus where the function needs to be analytic, and only then Laurent series will be applicable. So, the region of convergence of the series is modulus of z minus 1 lying between 0 and 2. That is what has been shown here. Now, at z is equal to 1 and z is equal to minus 1, the given function is not analytic, and that is why we enclose this point by this z minus 1 modulus greater than 0, this circle, and this is the point where function is not analytic. So, this distance is 2. So, in this annulus region function is represented by this series, and this is the region of convergence. In the outer part, when z minus 1 is greater than 2, there is no singular point outside this, and we can write down 2 upon z minus 1 modulus is less than 1, and in this region we can expand 1 over 1 plus z in this form. Here 2 upon z minus 1 is less than 1, so we can again expand in power series, and we will have 1 upon z minus 1 summation n is equal to 0 to infinity, and here we have minus 2 upon z minus 1 raised to power n, and the series will be minus 2 raised to power n divided by z minus 1 raised to power n plus 1, summation will take values from 0 to infinity. So, this series is convergent in the disk when z minus 1 is greater than 2. So, we have one representation inside the z minus 1 less than 2, and this is the representation when z minus 1 is greater than 2. So, we have two representation, and the Laurent series expansion this way is given as minus 1 over z minus 1 multiplied by z plus 1 is represented by this power series in this region z minus 1 lying between 0 to 2, and when modulus of z minus 1 is greater than 2, then we got this expansion. So, this is one example. In the next example, we consider function fz as z plus 1 divided by z minus 1. One may notice that this is analytic at z is equal to 0, it is not analytic at z is equal to 1, and function can be expressed in power series about z is equal to 0, because a function is analytic at z is equal to 0. This will be the Taylor series representation of this function. So, fz will be given by 1 minus 2 over 1 minus z, and this 1 upon 1 minus z can be expressed in powers of z, and we will have this expansion, and accordingly we will have this after simplification, and finally we will have fz is equal to minus 1 minus 2z 1 plus z square and so on, which will be convergent for modulus z less than 1, because about z is equal to 0, if we draw a circle, then if the radius becomes 1, then z is equal to 1 will be a singularity lying on the circle, and then the series will not be convergent. So, we say this series is convergent for modulus z less than 1. But power series for modulus z greater than 1 will be obtained as Laurent series, and for this we write down the denominator in the form as this. I have taken z outside. So, it is 1 minus 1 upon z in the denominator, and here we expand this also z can be taken out. So, it is 1 plus 1 upon z the numerator, and in the denominator is expanded as this, and what we have f z, if you multiply these terms, will be simplifying to this series, and further simplification will give me 1 plus 2 upon z plus 2 upon z square plus 2 upon z cube and so on, modulus z is greater than 1. And here you may notice that the terms are appearing in the denominator, or we have negative powers of z. So, it is a Laurent series expansion of the function, but it is valid for modulus z greater than 1. The power series, if we have to express the same function, but now in powers of z minus 2, then we may notice that this function is analytic at z is equal to 2. So, Taylor series can be used to expand this function, and again we simplify this term so that we can expand it in powers of z minus 2. So, we write down the function in this manner and then expand the denominator in powers of z minus 2, provided z minus 2 is less than 1, otherwise this will not be convergent. And then at z is equal to 1, function f z is not analytic. So, the distance between center z is equal to 2 and the point where function is not analytic is 1. So, that is why we say the radius of convergence for the series is r is equal to 1, and we have Taylor series expansion. But for modulus z minus 2 greater than 1, Laurent series can be obtained, and we have f z as z plus 1 divided by z minus 1. We again rewrite it, and since our domain is modulus z minus 2 is greater than 1, so we will now take z minus 2 outside, and we will have 1 upon z minus 2 in the denominator. So, simplifying this, taking q as 1 upon z minus 2 and modulus of q is less than 1, and expanding it, it is z plus 1 divided by z minus 2 in powers of 1 upon z minus 2. This is the geometric series, and simplifying it, it is z plus 1 multiplied by 1 upon z minus 2 minus 1 upon z minus 2 whole square and so on, and the region is z minus 2 is greater than 1, because after that there is no point where function is not analytic. So, this is the region of convergence for the Laurent series. Now, this example is slightly different. So far we have the function which we can use, we have functions and we are using geometric series expansion for obtaining the Laurent series, but in this example we will be using the Laurent series expansion and the formulae which we have derived just now. So, let us consider f z as sin z upon z square, and since f z is not analytic at z is equal to 0, so we consider the circle C modulus z is less than 1. Then in this circle we can write down f z as b n z minus a raised to power n plus summation n is equal to 1 to infinity C n z minus a raised to power n. So, this is in negative powers of n, and this series in positive powers of z minus a, and here we have to consider that mod z is positive, and the formulae for b n and c n, they are obtained as we have already done it. So, let us use this formulae to obtain b n and c n. So, accordingly it is 1 upon 2 pi I integral sin z divided by z raised to power n plus 3 dz. So, this is the formula for b n, and for c n the formula is 1 upon 2 pi I z into z raised to power n minus 1 multiplied by sin z divided by z square. This is my function fz. So, this simplifies to integrand z raised to power n minus 3 sin z dz, and 1 upon 2 pi is to be multiplied. So, this is the formula for Bn and Cn. So, since sin z is analytic, so Cn is equal to 0 for n greater than equal to 3. So, if n is greater than equal to 3, so these terms will not be appearing, and all Cn's will be 0 for n greater than equal to 3. So, we need to calculate only C1, C2, C3 etc. they are going to be 0. So, C1 is given by 1 upon 2 pi I z raised to power minus 2 sin z dz, and this is equal to 1 upon 2 pi I into 2 pi I sin z derivative divided by factorial 1. So, this is the formula which I will be making use of, and this derivative is evaluated at z is equal to 0. So, if you simplify it, this comes out to be 1, this and this will get cancelled, and derivative of sin z is cos z, which is evaluated z is equal to 0 gives me 1. So, this is C1. Similarly, C2 will be z raised to minus 1 sin z dz, and according to the formula we have 1 upon 2 pi I into 2 pi I into sine function evaluated at z is equal to 0 divided by factorial 0, and this comes sin 0 being 0, this comes out to be 0. So, this is C1 and C2 is 0. So, we will have z cube over 120 and so on, and it is convergent for modulus z greater than 0. So, this is Laurent series expansion for the given function fz. Now, we come to uniform convergence. Up to this point, we are using number of results. We are term by term multiplying series. We are integrating terms of the series and so on, without bothering whether this is possible or not. But here I will discuss uniform convergence of the series first, and then we will see that for power series this term by term differentiation and integration is possible. So, to define uniform convergence, consider a series of functions of z, and so we have n is equal to 0 to infinity summation f n z, which is f0 z plus f1 z plus f2 z plus fn z and so on. So, this series is considered. Let the sum converges for all z in a region G, and Sz be the sum of this series, and Snz is the nth partial sum of this series. Then convergence of this series means that we can find n for every given epsilon greater than 0 such that Sz minus Snz is less than epsilon for all n greater than n, capital N, which will depend upon the epsilon we choose and the point z at which the convergence of the function is convergence of the series is considered. This is the meaning of convergence. Note that n depends upon both z as well as epsilon. However, if we can find capital N which is independent of z for every given epsilon greater than 0 such that the difference between Sz and Snz, its modulus is less than epsilon for all n independent of z, it is a function of epsilon only, then we say that the series is uniformly convergent. So, accordingly, convergence is pointwise. That means, we say the series is convergent at z is equal to a, and uniform convergence is for a domain. So, we can find the capital N irrespective of z in that domain. So, uniform convergence is for a domain. Now, we establish a theorem regarding power series. We say that if we have this power series a n z minus a raised to power n, n is varying from 0 to infinity, that is a power series center at z is equal to a, then it has a radius of convergence r greater than 0. So, this power series will have a radius of convergence r greater than 0. If this is true, then this is uniformly convergent in the domain z minus a, which is less than equal to r for some r which will be smaller than capital R, that is the region of convergence. So, the power series a n z minus a raised to power n will always be uniformly convergent in this domain. Now, to prove this, let us consider S n z partial sum as a n z minus a raised to power n. It is a sum of n terms, so it is 0 to n minus 1. So, this is partial sum. Since each term in the series is continuous in z minus a less than equal to r, because each term of this series is a power in z. So, each term will be continuous in this region. So, we can say that a n plus 1 z minus a raised to power n plus 1 plus a n plus 2 z minus a raised to power n plus 2 and so on, plus a n plus p multiplied by z minus a raised to power n plus p. So, this is sum of p terms after a n. This is less than a n plus 1 raised to power r raised multiplied by r raised to power n plus 1, this being less than r, plus a n plus 2 modulus. These coefficients may be imaginary. So, we have to consider modulus here, and r raised to power n plus 2 plus, and the last term is a n plus 2 modulus into r raised to power n plus p. So, this sum is less than sum of these terms. So, the triangular inequality is applied. So, absolute convergence in z minus a is equal to r, which is less than r. So, we can say that n epsilon can be chosen for given epsilon positive such that this condition is satisfied for n greater than n epsilon. That means, we can find epsilon such that this condition is satisfied. We can find n such that this condition is satisfied. So, this is true for all z in this disk z minus a modulus less than equal to r, and for every n greater than n epsilon, and for p is equal to 1, 2 and so on. So, we can say that since n epsilon is independent of z, this follows the uniform convergence of power series. So, it does not depend upon z and the series is uniformly convergent. So, power series is uniformly convergent. Now, we consider this power series 1 plus z square plus z cube. This is geometric series, and we know that this fz minus snz, that is partial sum. The difference between fz and partial sum is z raised to power n plus 1 over 1 minus z modulus z is less than 1. This is the result which we have already established, and the geometric series is convergent at any given z. So, we can say that modulus of Sz minus Snz is equal to modulus of z raised to power n plus 1 over 1 minus z less than epsilon for all n greater than n. So, this is for a given z. Now, we say that if we consider z naught as slightly different point n plus epsilon divided by n plus epsilon plus 1. So, we can notice that still z naught is less than 1, but for this z naught we can say that z raised to power n plus 1 over 1 minus z, if you simplify this expression, this comes out to be this, and further simplification yields this, and from here we may notice that 1 minus x raised to power n is greater than 1 minus nx when x lies between 0 to 1, and this gives me z raised to power n plus 1 upon 1 minus z is greater than this expression. Or if we further simplify, we say z raised to power n plus 1 over 1 minus z is greater than epsilon. that means the n which we have considered will not work for this, especially when z is very close to 1. So, f z minus s n z is equal to z raised to power n plus 1 over 1 minus z greater than epsilon. So, geometric series is not uniformly convergent when z is very close to 1. So, there is a neighborhood, there is a region very close to z is equal to 1 where this condition is satisfied, and whatever n we have computed for given x will not work for a different z. So, this means that it is not uniformly convergent. However, if we apply the result of earlier theorem, then geometric series is uniformly convergent in z modulus z less than r. So, there exists some r which will be in which the geometric series will be uniformly convergent, but it will not be convergent throughout modulus z less than 1. There has to be some r in which this series is uniformly convergent. Now, if we consider different series which is x square plus x square over 1 plus x square plus x square over 1 plus x square whole square and so on, then for this series S n x some partial sum is 1 plus x square minus 1 over 1 plus x square raised to power n. Then we can notice that S n x tends to 1 plus x square if x is not equal to 0, and will tend to 0 if x is equal to 0. So, that means S x, that is sum of this infinite series minus the partial sum, is equal to 1 over 1 plus x square raised to power n for x is not equal to 0. But we know that 1 over 1 plus x square raised to power n modulus is less than epsilon, if implies that n must be greater than log 1 over epsilon divided by log 1 plus x square, and that means that this n we can choose for a given epsilon, and this depends upon x, and therefore n depends upon x, showing that the series is not uniformly convergent. So, this is a series which is not a power series. So, this is not uniformly convergent, but the earlier series was a power series. It will be uniformly convergent, but it is not uniformly convergent in a small neighborhood about z about modulus z is equal to 1. Now, if the series is uniformly convergent, then we try term by term differentiation of power series. So, for this we have a result which states that let f z is equal to a power series in powers of z minus a with non-zero radius of convergence, then f is analytic in a disk which is centered at a and of radius r. Then f dash z is equal to summation n is equal to 0 to infinity n times C n into z minus a raised to power n minus 1. So, if we term by term differentiate this series, we will get this, and this series is converging to the derivative of this function f of z. So, term by term differentiation is possible. Similarly, term by term integration of power series is also possible. Let f z is equal to summation n is equal to 0 to infinity f and z be uniformly convergent power series of continuous functions within a region G, and let C is a contour in G, then f z dz over integral over C is equal to summation n is equal to 0 to infinity and integral of f and z dz. So, this is the meaning of term by term integration. Now, let us prove this. Let the series f z is equal to summation n is equal to 0 to infinity f and z be uniformly convergent in a region G, and each term f and z is continuous at point z naught in G, then the function f z is continuous at z naught. So, we first prove this result and then we will prove the term by term integrability. So, let us consider S n is equal to f naught plus f 1 and so on, that is sum of first n terms, and remainder term is f n plus 1 plus f n plus 2 and so on. Since the series converges uniformly, that is been given to us, we can find n, which is a function of epsilon, for given epsilon greater than 0, such that r and z modulus of this is less than epsilon by 3 for all z in G. So, I have taken arbitrary value as epsilon by 3. So, this is by definition of convergence, and since Sn is sum of finitely many functions which are continuous at z0, this sum is continuous at z0. Therefore, we can find delta greater than 0 such that Snz minus Snz0. So, this is Sn is evaluated at z and this is at z0. This can be made smaller than epsilon by 3 for all z in G, provided we can find delta such that z minus z0 is less than delta. So, for this, in this disk, this difference will be less than epsilon by 3. This is coming from the continuity, and therefore, we can write down Fz minus Fz0 as Snz plus Rnz. This is for Fz, and for Fz0 I write Snz0 plus Rnz0. So, this will be less than Snz minus Snz0 plus Rnz modulus plus Rnz0 modulus. Now, this modulus is taken as less than epsilon by 3, and this is uniformly convergent. So, it is again taken epsilon by 3, and for z0 also we have also this also is less than epsilon by 3, and that makes Fz minus Fz0 is less than epsilon. And this proves that the difference is as Fz minus Fz0 is less than epsilon, and this proves that Fz is continuous at z0. Once this is done, we write down integral Fz over the curve C is equal to Snz dz over C plus Rnz dz over C. So, integration over C. So, this we can write, let L be the length of arc C. Since the series converges uniformly, we can find n such that for given epsilon greater than 0, R and Z is less than epsilon by L for all n greater than n and Z in G. This is due to uniformly convergence which is being given to us. So, R and Z dz integral and then taken its modulus will be less than epsilon by L. This we have taken, and this is length of the curve C is L. So, this is less than epsilon for all n greater than n, and this implies that integral Fz dz over the curve C minus Snz dz integral over C is less than epsilon. This proves our result that term by term integration is possible. On similar lines, we can prove the result which we have already stated, but haven't given the proof, that is the term by term differentiation of the series. So, we can go about this proof and the result can be reproduced. Now, we will discuss Weierstrass M test for uniform convergence. So, let us consider a series of positive terms, summation n is equal to 0 to infinity mn. So, we have m0 plus m1 plus m2 series be a convergent series. Then this series of functions f and z, n varies from 0 to infinity, that is f0 z plus f1 z plus f2 z and so on. So, this is again, this is another series. Now, we say that this series be a series such that for all z in a domain G satisfying this condition, that is f and z modulus is less than equal to m0 for all n. The idea is term by term, this term is smaller than this, f1z is smaller than m1 and so on. So, term by term, if you compare, then terms of this series are smaller than terms of this series. So, if that is the case, then if this series convergent, if this series is convergent, then this series will also be convergent. So, accordingly, summation n is equal to 0 to infinity f and z is uniformly convergent in G. So, if this is possible, then the series is uniformly convergent in G. So, this result can be used to establish the uniform convergence of given series. So, what we have to do is we have to find out corresponding m0, m1 etc., and if the resulting series is convergent, then this series is uniformly convergent. Once the series is uniformly convergent, then term by term differentiation, integration, etc. are possible. So, let us apply this to this geometric series. Fz is equal to 1 plus z square and so on, and we know that this is 1 minus z when modulus z is less than 1. So, therefore, for all z in this interval, in this neighborhood centered at z is equal to 0 and radius 1, we can find Fz is equal to f dash z is equal to 1 plus 2z plus 3z square, and we know that this series is nothing but 1 upon 1 minus z whole square, and we know that this is nothing but d by dz of 1 upon 1 minus z. So, the idea is this series is being uniformly convergent, and if we term by term differentiate this series and we get this sum of this series is this, we know from we can see that this is converging to this series, and we also know that this is nothing but derivative of this. So, this establishes the term by term differentiation of a uniformly convergent series. Similarly, if we integrate this series term by term, then on the right hand side we will have this series, and we know that this series is nothing but the series for minus log 1 minus z, and if you take its integral, it is nothing but 0 to z 1 upon 1 minus z. So, this also establishes term by term integration for the given function f of z. Viewers, today we have discussed Laurent series representation of a function. If the function is analytic in a domain, then we can represent this function in power series of z by Taylor series. But if the function is not analytic at certain points in the domain, then we can always enclose those points by a circle of some suitable radius. Then in the annulus region, if the function remains analytic, then we can represent this function by Laurent series. So, this is what we have done today, and apart from this we have discussed uniform convergence and term by term differentiation and integration of the series. Thank you.